Okay. Good evening, friends. Welcome to 360DigiTMG. Today, we are going to discuss about model compression, which is a very crucial technique in artificial intelligence, especially when we are deploying the advanced models on devices with limited resources. The goal of this model compression is to reduce the model size and complexity while keeping its performance as close to original as possible. Okay. So what we are doing here? So our main focus in compressing models is deployment on edge devices. So compressed models are smaller, which means they run faster and requires less storage. This makes them ideal for smartphones, wearables, and other devices where resources like memory and processing powers are limited. Then it is useful in reduced bandwidth costs. Smaller models take up less data, which means they are quicker to download and cheaper to transmit, saving on communication cost, especially in bandwidth sensitive applications. Then there is improved interference speed. With fewer computations needed, compressed models make faster predictions, enhancing the user experience with quicker response time. So, in short, what we are doing here in model compression, we are trying to, our goal of this model compression is to reduce the model size as well as keeping the model's performance as original as possible. Okay. Then, what are the model compression techniques? So, there are several. Few of them are, first is a quantization. So, in quantizations, this reduces the precision of the model's weight and activations. It makes more lightweight and efficient. Then there is operator quantization. In operator quantizations, this is a specialized form of quantizations, focusing on optimizing the specific operators within the model. Then there is GPTQ, which is Global Post-Training Quantizations. This technique applies quantizations after model is trained, which simplifies the deployment without needing the retraining. Then there is GGUF, that is Global Gradient Uniformity Framework. It is a newer method which focused on preserving the gradient uniformity during the compression to maintain the model accuracy. Then there is AWQ, which is the Activation Aware Weight Quantizations. This considers the activation when quantizing weights, leading to more accurate compressed models. Then there is distillation. Distillation is, here we are using the smaller models like student model. Learns to mimic a larger model like a teacher model. We want to achieve a similar performance as that of student with a lesser complexity. Okay. Then there is pruning. This technique removes less efficient parts of the model, resulting in the leaner structure without sacrificing too much accuracy. Okay. Then we'll see in detail about quantizations. So quantizations allows a model to execute some or all of its operation with reduced precision, often lowering the standard to 32-bit floating points values to 8-bit integer or even lower. This change results in a smaller model size and enables high performance vectorized out operations on the varieties of hardware platforms. To put it simply, what we can say, Quantization reduces the precision of weight and activations in the model. This makes the model representation more compact and decreases its computational requirement. So, which translates into the faster performance on resource constrained devices. Okay, so there are some key benefits by using the quantization techniques. So first of it is reduce the model size. It will reduce the model size. Quantization can reduce the model size by 4 times, 4x or more, making the deployment more practical on devices with limited storage. The devices which are having limited storage, it can be useful for them. Then faster interference speed. Models with reduced precision executes faster, leading to quicker precision and more responsive user experience. Then lower power consumption. Quantized model consumes less power, which is critical for battery operated devices. Then there is ideal. It is ports are ideal for edge development. Okay. So our quantized models are perfect for smartphones, wearables, and other devices that lack extensive computing power. Okay. Then there is how quantization works. So quantization works on 3 steps. First is our mapping values. Second is our representing values. And third is our computation. So in mapping values, we take our original 32-bit floating point values, which are mapped to the smaller sets of discrete values using a quantization scale and a 0 point. Then representing values. In weights and activations are stored. All these weights and activations are stored as lower precision integers like bit during the interference. Then computation. All arithmetic operation during interference are done using these lower precision values, drastically reducing the computational requirements. Then there are types of quantizations. So there is post-training quantization, which is PTQ. In post-training quantizations, it is particularly valuable because it can be applied to already trained models. It can be applied to already trained models without needing to retrain them again. So this means we can take a high precision, fully trained model and during the TensorFlow live conversion process, we can apply quantization techniques to make it faster and more efficient. Okay, so now there is benefits of post-training quantization. So first benefit is a ease of implementation. PTQ, that is post-training quantization, is a straightforward to implement as it doesn't require any modifications to the training process. Faster execution. By quantizing the model, we reduce the memory and computational demand, resulting in faster interference speed. Then there is smaller model size. PTQ, that is, post-training quantizations can significantly shrink the model size, making it much easier to deploy on devices which is having a limited storage. Then there is lower power consumption. With reduced computation, PTQ also lowers power uses, making it ideal for devices like smartphones and wearables that rely on battery power. So, this is the advantage of post-training quantization. Then there is again one more type of quantization, which is quantization aware training, QAT, which which is unlike a post-training quantizations, QAT incorporates quantizations directly into the training process. Okay. This means the model learns to handle lower precision at its training itself, making it more resilient when it deployed on edge devices with limited computational resources. Okay. Then there are several advantages of quantization aware training. So first of it is higher accuracy. QAT, which is quantization aware training, generally preserves more accuracy than post-training quantization, that is PTQ, because the model is trained with quantization reflects in mind. This makes it more robust when deployed with reduced precision. Within the training itself, we are learning the model. We are training the model in the learning phase only, so that it will learn the precision at its training phase. Okay, so it can give the higher accuracy. Then there is improved efficiency. Similar to PTQ, QAT reduces the model size and speed up interference through low precision computations, but often with even better performance outcomes. Then there is greater control. With QAT, we can fine-tune the model, balancing accuracy and compression to meet the specific deployment needs. Then there is dynamic quantization. Dynamic quantization is a technique that converts the model weight and activations to lower precision, specifically using integer representations. This process reduces the model size and allows for faster, more efficient operations on CPU and GPU as well. The key benefits of dynamic quantizations are it is used for improving the accuracy. So, unlike static quantizations or dynamic quantizations, can adapt to specific input data, preserving the fidelity to the original model. Enhance efficiency. By adjusting quantizations per layer based on the actual input values, it can improve memory uses and computational speed. Then there is flexibility. Dynamic quantizations can be applied to any trained model without modifying the training process, making it highly adaptable. So, this is the output from a QAT and PTQ. So, here we are using the quantized model, and here we are using the calibrated data, and we are using the calibration of that value. Okay, like fine-tuning that value. Okay, so after that, we'll get some output which will be represented to QAT quantized model, and here it will be represented as PTQ quantized model. Okay. Then there is GPTQ. GPTQ is a global post-training quantization, which is a highly efficient method for comprising large models after training, falling under the post-training quantization, which is PTQ. Okay. It is in the category of post-training quantization. The GPTQ, which is global post-training quantizations, is particularly valuable for massive models where full training or fine-tuning would be too costly. How GPTQ works now? So, it works on one-shot weight quantization. It works on minimizing the error. It works on calibration. So, let's see how it works. So in one short weight quantization, that is, it uses the GPTQ approximate second order information to quantize the weight in a single pass, which will make the process fast and accurate. Then there is minimizing error. Each weight is compressed in a way that it minimizes the mean squared error and it will preserve the model accuracy. Then there is calibration. So after quantizing, the model is calibrated by running interference on smaller data sets, refining the quantized weight for optimal performances. So, in instance, GPTQ enables significant model size reduction while maintaining the accuracy, making it an ideal choice for deploying the large models on resource-constrained hardwares. Then there is a GPTQ algorithm. It was introduced by Tranter in 2023, which is highly efficient post-training quantization method, which is trained for very large language models inspired by OBQ, which is optimal brain quantization methods. So GPTQ incorporates key optimizations that enables it to handle massive models. Then there are certain steps related to GPTQ algorithm. First is our arbitrary order insights. For large model, GPTQ leverages the finding that quantized weight in any fixed order yields the comparable performance. Therefore, GPTQ quantized all weight in the same order for each row of matrix, significantly speeding up the process. Then there is lazy patch updates. In lazy patch updates, instead of updating every column individually, GPT processes a patch of column at a time. For example, it will take, suppose, 1 columns at a time to update the weights, updating all those and a corresponding block of a matrix. After processing each block, a global update is applied across the entire matrix, which helps maintain the accuracy while improving the efficiency. So these steps allows the GPTQ to achieve high accuracy quantization with minimal mean squared error in the comprised weight, maintain model's performance, and in one-shot quantizations, it compresses the weight in a single pass, making it both time efficient as well as it is suitable for large-scale deployment. Then there is choke scale reformulations to tackle numerical inaccuracy that arises with the large models. GPTQ leverages the choke scale decompositions. This steps involves applying the decompositions to the Harrison inverse and adding a small dampening factor to improve numerical stability, and it will avoid computational resources as well. This reformation is critical for handling large-scale matrices accurately during quantization. So what we are doing here, we are taking for optimizing a large scale model, we are particularly using our massive large models where training or fine tuning from the scratch will be costly. So this method efficiently reduces the model size while maintaining the high accuracy, making it ideal for deployment on resource constrained devices. Okay. Then these are some of the steps. The full algorithm can be summarized in few steps. So first, we are using GPTQ algorithm begins with Choksley decompositions of Helison inverse, a matrix that helps decide how to adjust the weights. It then runs in a loop, handling matches of columns at a time. For each column in a batch, it quantises the weight, calculates the error, and updates the weight in a block accordingly. After processing the batch, it updates all remaining weights based on the block's error. The GPTQ algorithm was tested on various language generation tasks. It was compared with other quantization methods like rounding all weights to the nearest quantized value, that is RTN, nearest rounding value. Okay. Then there is GPTQ was used with the Bloom, which is the foundation model which we have seen earlier, which is trained on 176 billion parameters. OPT trained on 175 billion parameters. Model families and models were quantized using a single NVIDIA A100 GPU. Okay. Now, the key benefits of GPTQ can be high efficiency, like process the large matrices with minimal operational or minimum computation overhead and batch quantizing columns. Accuracy preservations. It will maintain model performance with reduced precisions. It will outperforming the simpler methods like RTN. Then there is single GPU compatibility, which achieves the substantial model compressions on large language models using 1A100 GPU, reducing resource requirements. Then there is GGUF, that is Global Gradient Uniformity Framework. So GGUF stands for Global Gradient Uniformity Framework. It's a method used to make training AI model more efficient and effective. So why do we need GGUF? So it is used for slow training. Like traditional training methods can be slow, especially for large models. This happens because some parts of the model might learn at different speeds, causing delay. Then there is uneven learning. When different layers or parameters in the model learns unevenly, it leads to inefficiencies. Some parameters may take longer to train or may not contribute much to final performance. Then there is, how does the GGUF help? So how does it help? It will take the faster training. It will take focus on important parameters. It will work on the smaller efficient models. Like GGUF aims to make learning process more even across all parts of the model. This means that all layers learns together at the similar pace, which will speed up the overall training time. Then it will focus on important parameters. Like not every part of the model is equally important for learning. Like GGUF helps identify which parameters are crucial. So the training focuses on those, avoiding wasted time on the less important ones. Okay. Then it will be trained on smaller efficient model. Like by optimizing the how models are trained, GGUF can allow for the creation of smaller models that still performs well. This is especially beneficial for running AI on devices with limited computing powers like smartphones. Then there is how GGUF works. So GGUF works on gradient analysis. So during training, GGUF clicks the size of gradients, the values that shows how much the model needs to adjust its parameter. Okay, like flowing through each layers and parameters. This will help identify which parts of the models are running effectively and which are not. Then there is adaptive learning grades. Based on the analysis of these gradients, GGUF changes the learning rates for each parameters individually. If a parameter has high gradient magnitude, meaning it's already changing a lot, it gets lower running rate. This is because it might not need as much adjustment. Conversely, what we can say, parameters with low gradient magnitudes indicates that they need more attention. Okay, so they will have a higher learning rate. This will help them learn faster. Okay, then there is smoother optimization. In smoother optimization, by adjusting the learning rates this way, GGUF will promote more uniformity in the size of gradients across the entire model. This leads to smoother optimization process. It can help the model reach its best performance more quickly. Then there is improved generalization. GGUF will help the model focuses on learning important features. Okay, that generalize the well to new unseen data. By prioritizing the parameters that need more learning, GGUF reduces the risk of overfitting. Yes. So where the model learns too much details from the training data and improves the performance when the model is applied to new examples. Okay. Then the key benefits of GGUF. So it is faster training. The first is that faster training. GGUF can greatly speed up the training process of AI models compared to that of the traditional training methods. By optimizing the how the model learns, it reduces the overall time needed to reach good performance. Then there is improved efficiency. GGUF smartly allocates resources to most important parameters. This means that the model can potentially be smaller while still performing just as same as that of as well as that of larger models, making it more efficient. Enhanced generalization. By focusing on learning the most relevant features, GGUF helps the model perform better on new, unseen data. This means it's less likely to overfit on training data and more likely to make accurate predictions in real world situations. Then there is dynamic adaptation. GGUF continuously adjusts to the changing needs to the optimization process. This adaptability allows it to fine-tune learning rates and focus areas throughout training, ensuring the model is always learning efficiently or effectively. Okay, so this is it for today. We have understood about few of the quantization models. We have understood how this model compression works. We have understood about the model compression techniques. Okay. Then we have understood about what is quantizations. Then we have understood how quantization works actually. Then we have seen some of the types of quantizations like post-training quantizations, quantization-aware trainings, dynamic quantizations, and then we have now understood GPTQ, that is global post-training quantizations. We have seen the algorithm with respect to GPTQ algorithm. Then we have seen GGUF, that is Global Gradient Uniformity Framework. And we have understood how GGUF works. Now we have seen the key benefits of GGUF. So this is it for today. Other parts we will see in the next of the lectures. Till then, goodbye. See you in the next